Dear grade 9 students, welcome back to the chapter Circles. Wishing you all a wonderful day, and let's get started. A theorem. Congruent arcs of a circle subtend equal angle at the center. Congruent arcs means arcs of same measurement. Let us see from the figure. Let RS be an arc and angle ROS be the angle at the center. And let AB be another arc of the same measurement as of RS, and AOB is the angle which is formed at the center. The theorem says that equal arcs will form equal angles at the center. For example, let us take this as 65 degree. This will also be 65 degree. That is a theorem. Equal arcs, equal angles at the center. Moving on to another theorem. The angle subtended by an arc at the center is double the angle subtended by it on the remaining part of the circle. So we have to focus on few things. We have to consider an arc. Let us see QR is an arc and QOR is an angle at the center. Angle at the center is double the angle which is formed on the remaining part. The remaining part means if you take the arc QR, we have to take the arc QPR, the remaining part of the circle. And remember, this is half, which means at the center is big and on the circle is small. And this is a very, very important theorem. We will use it in many examples later on. So for that, to prove this, let us consider the triangle POQ. Triangle POQ is isosceles. Can you say the reason? Very good. Because OP is equal to OQ, both of them are radii. So if this angle is A, this angle is also A. Now our intention is to connect between the angle QPR with QOR. For that, we have to consider the exterior angle QOM. So we can say angle QOM is equal to angle OQP plus angle OPQ. We have done this many times. Can you say the reason? Yes, exterior angle property. What is exterior angle property? If you have a triangle and an angle formed between an extended side and the triangle is called an exterior angle. This exterior angle will be equal to the sum of the opposite angles. Let's say this is A, this is B, then this angle will be equal to A plus B. So here both of these angles are A and A, so we can say this is 2A. Once again, considering the triangle POR is also isosceles triangle because OR and OP are radii. They are equal. And we can find the exterior angle, which is MOR. Angle MOR is equal to angle ORP plus angle OPR. Again, the same reason, exterior angle property. Now we need to consider the whole angle QOR. That is the angle at the center, which is from QOM and MOR will give us the angle QOR is equal to whole of this angle. This will be 2B. A plus 2B. But at P, we know that QPR is equal to only A plus B. So we can connect the relation. At the center, QOR is an angle at the center, which is 2 times A plus B, which is on the circle. So therefore, the angle which is formed at the center is double the angle which is formed on the remaining part of the circle. That is the theorem. Now let us consider the same situation in a semicircle. Let CB be a semicircle and CAB is the angle which is formed on the remaining part of the circle. Same way we can show that COA is an isosceles triangle and COM is an exterior angle, so this is 2A. Once again, BOA is an isosceles triangle, so angle MOB will be exterior angle 2B. So we can find that angle CAB is equal to A plus B and angle COB is equal to 2 times angle A plus B. Here we can see that COB is a straight line, so 180 degree. This is 180 degree is equal to 2 times what number? Which is 90 degree. So we found that this angle is 90 degree. Angle CAB is 90 degree. This will take us to another fact from this theorem, that angle in a semicircle is 90 degree. So whenever we have a circle with diameter, any angle which is formed on the circle, it can be at the point P, it can be at the point Q, or anywhere on the remaining part of the circle. If you have an angle, that all those angles will be 90 degree. Let's move on to the third part of the same theorem in a major arc. First we proved in a minor arc, then semicircle, now a major arc. Let RQ be a major arc. So the remaining part will be RPQ. So we are considering an angle which is RPQ. And we can show that the whole angle at the center, which is ROQ, the reflex angle, will be double of angle P. So angle ROQ, we have to use the word reflex because it's from the exterior part, is equal to 2 times angle P. And the theorem is angle formed at the center is double the angle which is formed on the remaining part of the circle. Moving on to another theorem. Angles in the same segment of a circle are equal. This is actually an extension of the same theorem that we just did now. Because if you have 2 points, let's say P and Q, we have the angle POQ at the center, then angle P and Q will be half of it. So we can say angle POQ is 2 times angle N. Again, let us consider another angle PMQ, which is formed on the remaining part of the circle. So again, POQ is equal to 2 times angle M. Left sides are equal, so we can say angle N is equal to angle M. This is the theorem, which means if you have 2 angles on the circle, which is starting from the same arc or same points, then all those angles will be of same measurement. If there's a 60, 60, 60. The only condition is it should be starting from the same points and it should be on the same side. It can't be on the minor arc. Then all of these angles will be of the same measurement. That's also an important theorem. Moving on to the next theorem. If a line segment joining 2 points subtends equal angles at 2 other points lying on the same side, subtends same measurement, which means if this is M and this is also M, the 4 points lie on the circle, which means if A is on the circle and the measurement of A and B are the same, then the angle B will not be in the exterior or in the interior. That's the theorem. Once again, if 2 angles of same measurement, let's say 60 and 60, and if they are on the same side of the circle, then both of these points will be on the circle, not in the exterior and not in the interior. Such points which are all on the circle are called concyclic points. Moving on to another theorem. The sum of either pair of opposite angles in a cyclic quadrilateral is 180 degree. First of all, we need to know what is a cyclic quadrilateral. Cyclic quadrilateral is a quadrilateral with all the 4 vertices on the circle, not in the interior, not in the exterior. It will be on the circle. Before we have studied about circumcircle. It is a circle which is passing through all the 3 vertices of a triangle. Such a circle is called circumcircle. Here, cyclic quadrilateral means all the 4 vertices are on the circle. Now the theorem says that the sum of the opposite angles will be 180 degree. Angle P plus angle R is 180 degree. Remember, opposite angles, not on the same side. And angle Q plus angle S will also be 180 degree. We just have to prove one pair, because the other pair definitely will be 180 because we can subtract from 360 degree. And when you add all together, we will get the total 360 degree because total angle in a quadrilateral is 360. So if this angle is 100, then this will be 80. That is the theorem. Now, the converse of this theorem. The converse of this theorem says that if the sum of the opposite angles is 180 degree, we just have a quadrilateral without a circle. If when you add them, it is 180 degree opposite angles, then this will be cyclic quadrilateral, which means around a square and around a rectangle, we can draw a circle always because they are 180 when we add the opposite angles. That is a fact that we can derive from the same theorem. Let us see an example here. AB is the diameter of a circle. CD is a chord equal to the radius of the circle. CD is equal to the radius. We know these two are already equal. So triangle COD is equilateral now, because OC equal to OD are radii and CD is equal to the radii they already given. So all the 3 sides are equal. So this is an equilateral triangle, and we know that in an equilateral triangle, all angle equal to 60 degree regardless of the size of the triangle. Each angle is 60, 60, 60. Now, our question is to show that angle E is 60 degree. For that, let us consider the angle ACB. Angle ACB is 90 degree because that is an angle in a semicircle. Angle in a semicircle is 90 degree. Therefore, angle ECB is 90 degree. Linear pair, because these two forms a straight line. Now, coming to the point of angle E, we have to consider the triangle ECB. Angle ECB is 90 degree. Plus angle E is missing, which is AEB, plus angle DBC. Altogether, we will get 180 degree angle, some property of a triangle. We know ECB is 90 degree. This is missing, we have to find. What about DBC? DBC. This angle is easy to find out now because you have the angle O. So we can say that angle DBC is equal to half of angle COD, because they are the angles on the same side of the segment CD. And we have seen the theorem, angle at the center is double the angle on the circle. On the circle is B, and at the center is which is 60. So this is double of on the circle, so this will be 30 degree. So we found out this is 30 degree and this is 90 degree. So From equation 1, we get 90 degree plus angle AEB plus 30 degree is equal to 180 degree. Therefore, angle AEB is equal to 180 minus 120, which is 60 degree. That was to be proved. So we found this is 60 degree. Moving on to second example. ABCD is a cyclic quadrilateral in which AC and BD are its diagonals. That angle CBD and angle CAD are from the same segment. So they will be equal. This is 55, so this is also 55. We can see angle DAC is equal to 55 degree because angles in the same segment are equal. BAC is 45 degree. So total angle DAB is equal to 45 plus 55, which is equal to 100 degree. This whole angle is 100 degree. And we know this is a cyclic quadrilateral. So quadrilateral ABCD is cyclic because vertices are on the circle. So the opposite angles will be 180. Angle A plus angle C will be 180 degree. At the point A, we found it is 100 degree plus the angle C, which is BCD, is equal to 180 degree. Therefore, angle BCD is 80 degree. That was the question, to find angle BCD. Let's see the third example. Two circles intersect at 2 points A and B. AD and AC are diameters of two circles. Prove that B lies on the line segment DC. To show that DBC is a straight line, we can show this is 180 degree. That's enough to show that angle ADB and angle ABC are 90 degree. It's so easy to prove because AD is the diameter. So DBA is angle in the semicircle. Angle ABD is equal to 90 degree because angle in a semicircle is right angle. Same way, angle ABC is also 90 degree, same reason in the second circle. Now when we add both this, we will get ABD plus angle ABC is equal to 90 plus 90, 180. Therefore, DBC is a straight line. Or we can say B lies on the line segment DC. Moving on to another example. ABCD is any quadrilateral and they gave the angle bisectors. AF, BF, CH and DH are the angle bisectors. Then we have to prove that the quadrilateral formed in the middle is cyclic, which means we have to show that opposite angles when you add, you will get 180 degree by theorem. If you prove F plus H is 180, this is cyclic quadrilateral. Now the given condition is each of the angle bisectors. Each of these line segments are angle bisectors. So in triangle AFB, half of angle A, we need to take this angle which is half of angle A, half of angle A plus half of angle B plus angle AFB is equal to 180 degree, angle sum property. So what is AFB now? 180 minus half of angle A plus angle B when you move these to the other side. But we know that AFB is the same as EFG. So we get EFG is 180 minus half of A plus B. Let this be equation 1. But we can replace this angle here. Now in triangle DHC, also we get the same condition, half of angle D plus half of angle C plus angle DHC is equal to 180 degrees, same reason. Therefore, angle DHC is equal to 180 minus half of angle D plus angle C. But DHC is the same as EHG. Angle DHC is equal to angle EHG. So we can replace EHG here. And this is equation 2. From 1 and 2, we get the answer that EFG is 180 minus half A plus B, and EHG is 180 minus half D plus C. So we add them. 1 plus 2 will give us angle EFG plus angle EHG is equal to 180 minus half A plus B plus 180 minus half C plus D. 180 plus 180 is 360. Let's continue here. So 360 minus half of A plus B plus C plus D. So which is another 360, half of 360. 360 minus 180. Therefore, these two angles will give us 180 degree. Angle F plus angle H is these two angles, 180 degree, which means EFGH is cyclic quadrilateral. That's what we have to prove. That's all for this period, and we will continue with the exercise in the next period.